Now we prove the if part of this theorem, that is, for any open set in Rn, U, the pre-image of U is opened in Rn, then we want to show that F is continuous. Okay. For this purpose, record that our F is a map from the open set A to Rn. We want to say that F is continuous. This means that for F is continuous at every point in the set A. So we take a point A in this set. We need to prove that F is continuous at A. Okay? We need to prove that F is continuous at A. So FA we denote by B. The image of A under the map F. FA belongs to Rn. And for any epsilon positive, we notice that the epsilon neighborhood of B is open. We have proved previously that any balls are open sets. Okay, so this is open. Therefore, by our assumption, the pre-image of this ball, the epsilon neighborhood of B, is open. Of course, this epsilon neighborhood of B is opened in Rn, but its pre-image is a subset of Rn, which is also opened by our assumption. So by our assumption, the pre-image of this ball is opened in Rn. And A contained in this ball, right? Because FA equal to B belongs to the epsilon neighborhood of B. So A belongs to this set. Therefore, A is an interior point of this set. And also A, of course, A is a point in A. So actually A belongs to the intersection of these two sets. But because A is opened, the pre-image of the epsilon neighborhood of B is also opened. Therefore, the intersection is opened. So this is open. An open subset of Rn. Therefore, A is an interior point of this open set. So there exists epsilon positive such that the epsilon neighborhood of, no, not epsilon. We should say there exists delta positive such that the delta neighborhood of B, of A, contained in this open set, the intersection. And this intersection is obviously a subset of the pre-image. This implies that the image of the delta neighborhood of A is contained in the image of the epsilon neighborhood of B, but B is FA. So this implies that F is continuous at A. Remember, we have result previously that if this is satisfied, then F is continuous at A. Or you can consider this as follows. we have known that this is contained in, okay, so this means if x belongs to the delta neighborhood of A, that is to say the distance between x to A is less than delta, then fx belongs to the image, therefore belongs to the epsilon neighborhood of Fa. So this is equivalent to fx, the distance from fx to Fa is less than epsilon. So if the distance from x to A is less than delta, then the distance from fx to Fa is less than epsilon. So this is to say, this means f is continuous at A. Okay, so the theorem is completely proved. Okay, now I will give some remark about this theorem. So this theorem says that the continuity of a function or a map can be described by open sets. We don't need to consider distance. So this is the starting point of topology, another subject very important in mathematics. Describing continuity via open sets lead to topology. Important area in mathematics. Okay, this is our first remark. That is to say, for a non-empty set, you choose some subset, call them open set. Then you can talk about continuity of such space called topological space. Then you can talk about continuity of maps from one topological space to another topological space. So this is topology. This should be a course you will learn in later semester. Okay, so we don't want to go to more details about topology, but I just want to remind you that in chapter 12 of our textbook, which is about metric space. Metric spaces are special cases of topological space. Okay. In metric space, we have distance, so we can define open sets just like what we have done in Euclidean space. Having defined open sets, metric space become topological space. And our Euclidean space is also a special case of topological space. Of course, Euclidean space are also metric spaces. Okay. Now, I will give you another remark. In this theorem, we use the open sets to describe continuity. According to the De Morgan law, open set has a closed relation with closed sets. Therefore, we can dually using closed sets to describe the top continuity. So we have a proposition, maybe. That is to say, now we need to assume that A is opened, A is closed. Then, no. F is a map from A to Rm. Then, F is continuous if and only if the pre-image of any closed subset of Rn is closed for all closed. Maybe I write here. So F is continuous if and only if the pre-image of F and closed subset capital F of Rm. So we just proved F is continuous if and only if any pre-image of open set is open. So this proposition tells us that we can also say this: F is continuous if and only if the pre-image of every closed subset is closed. Okay. This follows from the previous theorem and the Morgan law. Because open set has close relation with closed sets. But we can also prove this proposition directly without using the previous result about open sets. Now I will show you what to do this. How to do this. So this is if and only if. Therefore, we need to prove two directions. First, the only if part is easy. Only if part. We know that F is continuous, and we take F closed set in Rn. We want to prove that its pre-image under our map F is closed. Therefore, we suppose xk is a sequence in the pre-image of this set capital F, and xk converts to A. To see that the pre-image is closed, we need to show that any such sequence implies that the limit A is in F. We want to prove that A is also in the pre-image of capital F. This is what we want to prove. Can this be true? It's easy. Because F is continuous. So F is continuous at A. Therefore, by the continuity of F, Fxk will converge to Fa. Okay? But we also know that Fxk, we also notice that Fxk belongs to capital F. Because xk is taken from the pre-image of capital F, so Fxk belongs to F. So, but F is closed. So this conversion implies that Fa belongs to F. Therefore, A belongs to the pre-image of F. So from the continuity of our map F, we have proved that the pre-image of any closed set in Rn is closed in Rn. Okay.